Good day, everyone. I hope you guys are doing well. I hope everyone is doing good. Today, we are going to do the rate and extent of reactions as we discussed in class. What is the rate and extent reaction? So there are two types of reactions that we're going to discuss in this case. The first one is endothermic reactions. These are reactions that take up energy or transfer heat energy to potential energy. And with endothermic reaction, more energy is absorbed than released, and new bonds are weaker than the bonds that are broken. And the other reaction that we're going to talk about today is the exothermic reactions, which are reactions that release energy or transfer potential energy to heat energy. And with exothermic reactions, more energy is released than absorbed, and new bonds are stronger than the bonds that are broken. And since we're talking about the transfer from heat energy to potential energy or potential energy to heat energy, what is the energy required? So there is a minimum energy that's required for a reaction to take place, and this reaction is known as the activation energy. And the activation energy is represented by EA. So this is what activation energy is. And also, in this case, since we're talking about energy, we will talk about the reaction rate, or the rate of reaction. And the reaction rate indicates the change in the concentration of the reactants or the product per unit time. So, the average rate of reaction describes how quickly reactants are used or how quickly products are formed during a chemical reaction. And there is an equation that you can use to calculate the average rate of reaction rate. The use of a reactant equals to the moles reactant used divided by the reaction time, or the formation of the product equals to the moles formed divided by the reaction time. So there is theory that we need to take note of, or you need to explain how to describe it or how to explain it when in terms of rate of reaction. And this theory is called the collision theory, which is the reactant particles must collide with the correct energy and correct orientation for the reactants to change into products. In other words, it means that for this reactants to change into products, the particles in the reaction or in the reactants must have the correct energy, and they must have the correct orientation. And there are four properties of the collision theory. The first one is the effective collision. The second one is the frequency collision, and the energy of the particles, and the correct orientation. So this is the summary of what the rate of extent and reaction is about. So we're going to discuss some few questions today, or some few examples. The first example says, name two factors determining whether a collision is effective or not. So the first one, as I've just mentioned, is that for the particles and the reactants, for them to be converted into the product, they must have the correct energy, or they must have an energy that is equal to the activation energy, equal or greater than the activation energy, and they must also have the correct orientation. So those are the two factors that will determine whether a collision is effective or not. And the second example that we're going to discuss today is, consider the following chemical reaction. You have 100 grams of zinc granules and are added to a 500 ml of hydrochloric acid. Describe how each of the following changes will affect the reaction rate. Write down only increase, decrease, or remains the same. So as we have seen, we have a chemical reaction going on. We have 100 grams of zinc granules, which is added to 500 mils of hydrochloric acid. Now we ask what will happen to the rate of the reaction when these changes are made. A, zinc powder with the same mass is used instead of zinc granules, which means that what will happen to the rate of reaction? It will increase. Why? Because zinc powder has a great surface area than the granules, which means that there will be a good orientation for the particles to collide, hence, or it will be easier for the powder to dissolve than granules. That will make the reaction rate occurs faster, or the orientation will be higher, hence it will increase the rate of the reaction. B, what will happen if the reaction mixture is heated? The reaction rate will increase when the reaction mixture is heated because when you boil something, the particles of that mixture will become excited and they will have high energy. And with high energy, we just mentioned that for a reaction to occur or for reactants to be converted into products, they must have an energy equal to or greater than the activation energy. And when the mixture is heated, it means that the particles in the mixture will be excited and they will have a high energy, hence the reaction rate will increase. And C, it says what will happen to the reaction rate if 750 mils of the same solution of hydrochloric acid is used instead of 500 mils. So the reaction rate will remain the same. Why? Because the reaction rate is independent of the volume of the reactant. So as much as you can increase the volume of the reactant, the reaction rate will still remain the same. And C says what will happen to the rate of reaction if copper shavings are added to the reaction mixture. So now we take as if like we talk about zinc, that you have zinc granules already, but now if you had to add another reactant, which is copper shavings, obviously they're not granules, they have a good surface area than the granules. It means that it will increase the correction orientation or the orientation of the reaction or reactant, hence it will cause the reaction rate to increase. So these are some of the example of how you can know how the reaction rate is affected and what determines a good collision and which does not determine a good collision. Now let's move to the next question. The second example that we're going to discuss is how to calculate the rate of reaction. And the question says, initially the concentration of the reactant, hydrochloric acid, in a reaction vessel was 0.1 mole dm per cubed. After 3 minutes, it has decreased to 0.04 moles dm per cubed. What is the rate of the reaction? What is the first thing that you do when you have a question like this? Is to identify what you are given. Initially the concentration, so we are told the initial concentration to be 0.1, and after 3 minutes, so we're given the time, it has decreased, meaning the concentration decreased from 0.1 to 0.04. Now we know what is the final and the initial concentration. We know what the time is. We are asked to calculate the rate of the reaction. And the equation we're going to use is the rate of reaction equals to the change in the concentration of hydrochloric acid divided by time. We know that the final concentration is minus the initial concentration divided by time, and this represents the change in the concentration of hydrochloric acid. Now you just substitute what you're given. You have 0.04, which is the final concentration after the time, after 3 minutes, which decreased to 0.04 minus the initial, which is 0.1, divide by 180 seconds. So you must remember to convert your time. It was given in minutes, so you must convert it into seconds by saying 3 times 60 seconds, which will be 180 seconds. And in this case, you will get your rate of reaction to be 0.0033 moles per dm cubed per second. So this is an example of how you can calculate the rate of reaction when you are given the final and the initial concentration and time. So this lesson helped us to know about the rate of reaction. So in our next lesson, we're going to discuss more about the potential energy diagrams and how the endothermic and exothermic reaction works. But for now, I will end here. So bye everyone.